Hello students, in this video we are going to continue our study of Cauchy-Riemann equation. So if you remember, okay, let me recall. Let's say that we have a function, right? So for now I'm just writing f is from C to C, yeah, C to C, yeah? And is a given function, is a differentiable function. We have talked about what differentiable function is. Differentiable function. So what does it mean? It means that the function is differentiable for all points in C. Yeah? Differentiable function. Now, generally speaking, we do not have to have f from C to C. Huh? So we can also write f is from omega subset of C to C. To C. Okay, this is the general framework, and where omega is a open set. So all of this, what I am doing, you can do it for f from omega to C. Yeah, okay, and that is the most general part of it. But anyways, I am going to write it from C to C, but you can just assume it from omega to C. Yeah. Now the thing is this: it is a differentiable function. What did I tell you? If you remember in the last video, what we did is, if the function is differentiable, yeah, then what we can say is it satisfies. So you see, f of z, right? F of z, that will be, see, if we take z, which is x plus iy, right? X plus iy from the complex number C. Clear? If we take that, then f of z is also in C because f is from C to C. So this is equals to w. Yeah. So if it is a complex number, that w, that depends on z. You see, that w depends on z, right? It changes with z. So I can write it as a function whose real part depends only on x and y, plus there is a imaginary part which depends on x and y, right? This is what we did. Okay, and if it is differentiable, if f is differentiable, then what we have is u of x equals to v of y, and v of x is equals to minus u of y. Okay, what does this mean? See here, we know what real differentiability is, right? So let's say f is from R2 to R. Let's just assume that R2 to R. For such a function, we know what differentiability is, what this idea is doing. But here the concept of differentiability is, I mean, in terms of partial derivatives and directional derivatives, right? Here we are defining the derivative in terms of, you know, R2 R, that same sort of idea, what we did in the last video. And then because that's a complex differentiation, we are just using our idea of real differentiation to actually get an equivalent statement. So in this case, ux equals to v of y and vx equals to u of y. Why this is true? Because you can see that here u is again u and v. These are functions from R2 to R. Okay. I hope this is clear to you. Yes, and this is called the CR equation. Yeah, if you remember, this is called the CR equation. Now we are going to now the question is this. See, what did we do? We did that differentiability. Yeah, if the function is differentiable, it means that it satisfies the CR equation. Yeah, equation. Now the question is this. Let's say it satisfies the CR equation. So essentially, what we have is the other way around. And is this true? Is this true? Is this true? That's the question. Huh? Okay, let's just put it this way. Now we have this theorem, and it's a very, very simple theorem. So let me write it down. So another theorem. This is the converse of it, theorem. Okay, what does that theorem say? It says that let f of z, which is u of xy plus I times v of xi, okay, xy, be defined. Okay, this I already defined. There is no point writing it, but maybe I can write it down. See, I think this will be fine. Maybe I can write it down. Yeah, let me write it down. Let f of z equals to ux plus I v z be a given function. Okay, so essentially what we are trying to do is we are going to see that if this function turns out to be a differentiable function or not, right? So let's say this is a given function such that the real part and the imaginary part. What is the real part? U of xy, and what is the imaginary part? V of xy. Okay, those two, and V of xy v of x comma y, these two real part and imaginary part, have continuous first order derivative, partial derivative, continuous first order partial derivative, first order partial derivative. Here derivative, okay, that satisfies the CR equation. That satisfies the CR equation. Okay, that satisfies the CR equation. In, let's say, here I am doing it for in a domain omega subset of C. So it's, omega is a domain, omega is a domain. Okay, if it does, then f is differentiable in omega. I hope this is clear. See, initially what we are saying is this: f is differentiable. F is differentiable means f prime z is ux plus I vx. We already know, right? And you can also replace this thing, right? I mean, you can replace it with y if you want. Ux is vy, so it is vy minus I times uy. Okay, you can write it this way also. So basically, what we are saying is this: if f is differentiable, f prime of z can be written as ux plus I vx. Yes, and f prime z exists, so all of this particular thing, the real part and the imaginary part, should exist here. Now the question is this: what about the other way? So let's say that the CR equation is satisfied, right? Now can we say that the function is differentiable? This theorem says that yes, you can, given that u and v has all partial. So basically, you see, u has partial derivatives ux and uy, right? And v has partial derivatives vx and vy. What this theorem says is all these partial derivatives must exist and they are continuous. Okay. So those partial derivatives has to be continuous, not the function itself. The function has to be, but even that, the partial derivatives has to be continuous. Clear? I hope this is clear. Okay. So that is differentiability. Now, there is a small remark which I want to put, and I want you, this is kind of not a remark, it's basically a question. Let me put it this way, question. Okay. Question. So, you see, let's say f is differentiable in omega. Yeah. Does that imply, let me put it in a question, that f is continuous in omega? Okay. What is the hint? The hint is this: think of your function from R to R, right? So the definition of differentiability is exactly the same as what we are doing here. Yes. Now the definition of continuity from R to R and the definition of continuity from C to C is essentially the same, right? So, and in R to R case, the function, if it is differentiable, it is going to be continuous. So what happens here? Yeah, that's the question. Okay. So we have this now. Let me, so the proof of this theorem. So essentially what we are saying is this: if f of z can be written like ux plus I vx, where u and v has first order partial derivatives and it satisfies the CR equation, yeah, then we have the function has to be differentiable. Yeah. Okay. Let us look at an example. The first example. The first function which we know to be differentiable is z or z square, right? Let's start with z square. Z is in C. So z is x plus iy. Yes. So here, let us break up into u plus iv. So f of z is u of xy plus I of vxy. Yeah. So if we write it down, it becomes x square minus y square plus I times 2xy. Clear? So you see here, we already know it is differentiable, but I am going to see if the theorem also holds or not. The theorem says that it has to have first order partial derivative. See, in this case, what is ux? Ux is nothing but, it's very easy, it is 2x, right? And what is uy? Uy is minus 2y. What is vx? Vx is 2y and vy is 2x. Okay. Now, clearly, you can see that clearly u and v has first order partial derivatives, first order partial derivatives. Huh? Sorry, U and V has continuous partial derivatives. Huh? So basically, all the partial derivatives are continuous and satisfies CR equation. And satisfies CR equation, right? Satisfies CR equation. CR. So essentially, this is differentiable. You can also use this theorem to prove that. Okay. So let's look at another example. See, let's say fz. What is one function which we know is not differentiable? If you remember, what about mod z? Let's look at this function. Yeah, is it differentiable? We have already seen in the last video it is not differentiable. So this is z is x plus iy. Yeah. In the last video, I did it for x square, but you can just write it as mod x also, absolutely no issue. So let's write it as mod z square. Let's do this. Yeah, fz equals to mod z square. So now you see, therefore fz you can write it as x square minus y square, sorry, plus y square. Yeah, this we have did, right? We did that. This is differentiable. We already know that. So here, and what is the imaginary term? Plus I times 0. So therefore, u of xy, we can write it as x square plus y square, and v of xy, we can write it as, and v of xy is 0. Okay, now let's check. Of course, this does not satisfy CR equation, so there is nothing to show. So essentially, does not satisfy CR equation, does not satisfy CR. Okay, and hence this is definitely not differentiable. Okay, so the proof of this theorem, the proof of this particular theorem, that if first order derivatives exist and they are continuous with and satisfy the CR equation, then this is differentiable. This particular theorem, the proof I am not going to do because this is a little complicated proof which is out of the syllabus. Okay, so the proof we are going to skip, but always remember, you just have to show this thing. Yeah, please remember this thing. Let me put it this way. Remember, you write f is u plus iv, okay, and show that u and v both has partial derivatives. They have partial derivatives. Let's say those partial derivatives must exist. They are continuous, yes, and satisfy CR equation. Just this particular two things: the partial derivative exists and it is continuous for both u and v, and the CR equation is satisfied. That's all. That guarantees that the function is differentiable. Okay. So let's look at another very, very important remark. This is a very, very important remark. Please remember this remark. So what does it say? It says that an analytic function, I am going to look at this particular example and write down this remark. An analytic function, differentiable function, let me not put it analytic, a differentiable function, okay, of constant absolute value, okay, is constant. Okay, this is a little, maybe a little vague statement. So what I am basically trying to tell you is this. Let's say if f is differentiable, in omega, such that mod f of z is equals to, let's say, 1, or any other constant, doesn't really matter, for all z in omega, let's just say, then f of z has to be constant throughout omega, constant in omega. Is it okay? This is very, very simple statement. So let's just look at how this thing works. Okay, so this is a small remark. Okay, so let's say that f can be written as u plus iv, right? So since f is u plus iv, mod f. Mod f is mod of f of z. I am writing it like this. This is u square plus v square. U square plus v square. That is equals to 1. Clear? That is equals to 1. Okay. This is by, so basically the constant I am assuming it to be 1. You can take it to be, okay, anyways. I mean, you don't have to take 1. Let me take it to be a constant k. It's a constant. Okay. Now, you see, if this is true, then we can use differentiation here, explicit implicit differentiation. So it becomes u ux plus v vx is equals to 0. Okay. And u uy plus v vy is equals to 0. Okay. This is always true. Now, you see, if it is a differentiable function, we already know that CR equation is satisfied. So, therefore, since ux equals to vy and vx equals to uy, vx equals to uy, one has ux, and this vx I am going to replace it by uy minus vuy equals to 0. Here, and from the second part you have uy. This I am keeping it to be uy, and then I have vy. This I am going to write it as ux plus v times ux is equals to 0. Okay, so you have 2, 1, and 2 equations. Yeah. Now, okay, so this is true, right? U square plus v square ux equals to u square plus v square uy is equals to 0. Yeah. Now, of course, if u square plus v square, this constant, this is equals to constant, right? And if the constant is equals to 0, that will of course imply u equals to v equals to 0. There is nothing to prove. Yeah, because sum of two square functions, real functions these are, right? This is equals to 0, so that will give you u equals to v equals to 0. That will imply f is 0. So that's a constant function. If u square plus v square not equals to constant, which is not equals to 0, what does that imply? It will imply that ux equals to uy equals to 0, and that will imply that is equals to vx equals to vy. Very Cauchy-Riemann equation, right? Ux equals to minus okay, v minus u. Yeah, there's a minus here. Okay, minus v. Yeah, so that will imply that u equals to v is equals to constant. Okay, and hence, therefore, if u and v are both constant, that will imply that f is constant. Yeah, constant. Okay, so that is the main idea of this. Okay, so what did we show? We showed that if you have a differentiable function which is basically of constant absolute value, that has to be constant. Fine. Now let's look at something called another criteria, which is a very, very important criteria. This is called Laplace equation. So what does it say? It says that, let's say, if f of z equals to u of xy plus I v of xy, okay, is differentiable in a domain omega. Okay, as I told you, whenever I am writing omega, you just assume which is the domain. Then u and v satisfies the following. See, we already know that if it is differentiable, it always satisfies the CR equation. Yeah, but it does more. It satisfies this thing. uxx plus uyy equals to 0. This we write it as Laplacian of u. So basically, in this case, Laplacian of u is 0, and vxx plus vyy is equals to 0. This we called as Laplacian of v. So essentially, what we are saying is this, the real and the imaginary part, of course, they satisfy the CR equation. Yeah, that we already proved. It does more. What it does is it actually satisfies something called Laplace equation. This is called Laplace. So this is called Laplacian. Laplacian. We write it like this. So it satisfies Laplacian of u and Laplacian of v is equals to 0. Yeah. So and have continuous second order partial derivative. And not only first order. See, in the last, we just showed that if it is differentiable, the ux, uy, vx, vy, all those exist and they satisfy the CR equation. Here we are saying that much more. We are saying that not only these, u and v satisfy something called a Laplace equation, which is uxx plus uyy equals to 0, and vxx and vyy equals to 0, and not or, and both are satisfied. And thing is, those partial derivatives, so basically they are continuous. So basically u, v, they have second order partial derivatives which are continuous. Yes. Okay. So how do you prove something like this? Let's look at the proof. This is a very, very simple proof. Yeah. So throughout this course, whenever I'm writing the proofs of this thing, generally speaking, the easy theorem proofs I'm going to do. The difficult theorems, I will just give you some ideas. Okay. Because those proofs may be very complicated for this particular course. Okay. So see, if it is differentiable, what do we know? We know that the CR equation is satisfied. So if its CR equation is satisfied, ux equals to vy and vx equals to minus uy. Yeah. So if ux equals to vy, now let's say if we take a partial derivative of this particular thing, that will imply uxx equals to vxy. Yes, and uyy is equals to vxy minus vxy, right? So here, from here, you take this with respect to y, so you get this. Okay. Therefore, you see uxx plus uyy is nothing but 0. See, very, very simple, right? Yeah. So that is what. So essentially, what we are going to have is this satisfies. This is nothing but the Laplacian of u. And similarly, we can also show that Laplacian of v is going to be 0. Is this okay? Yeah. And what the thing is, this is the small question which I want to put it, and this I want you to do. You can also show that it has second order partial derivatives. So please show that. So these partial derivatives which you have, they are continuous. Show that they are continuous. That they are continuous. They are continuous. Okay. I hope this is clear. Right. So what do we have? A function which is differentiable. They satisfy the real and the imaginary part satisfies the Laplace equation. Okay. Right. So you see, there is this small remark. Let me put it as a small remark. If f can be written as u plus iv, then v is said to be the harmonic conjugate of u, and vice versa. Harmonic conjugate of u. See, basically what I am trying to say is this u. If f can be written as real plus the imaginary part, u plus iv, yeah, they have some sort of relation. They may look different as a real part and an imaginary part, but since they are put together using a f, so basically f is u plus iv and f is differentiable. That actually says something about u and v. They have a relation between them. They have a very specific relation in the sense that v has to be a harmonic conjugate of u, and the other way is also right. Okay. So let's look at what exactly does that mean. So let's look at an example of it. So let's say that u of xy is equals to x square minus y square. Okay, and maybe just put it minus 2x. Yeah. So let's say given this u, yeah, can you? So the first question is this question. First question Q1. Can we Can we build a harmonic function? Sorry, differentiable function. Sorry, not harmonic. Can we build a differentiable function? Using u as real part. Okay. And the second question is this, that if possible, find the harmonic conjugate. Harmonic conjugate of u. Yeah. Okay. So first thing first, how do we show that these? We want a function f. So basically, we want f which looks like x square minus y square minus 2x plus I times vxy. Here. Okay. And the thing is, I want this function is analytic. This is the question. We want this to work. Okay. Okay. So first question. So answer to the first question. First answer. See, if let's say this function is differentiable, what do we know? What is u of xy here? U of xy is nothing but x square minus y square minus 2x, right? So in this case, what happens? We guarantee that it satisfies, of course, the CR equation and all those things are there, but it also satisfies the Laplace equation. So what happens is u, if it is differentiable, sorry, not let me put it as differentiable, is differentiable. Okay. If we, so in this case, what happens is uxx plus uyy has to be 0, right? So first of all, let's just find out what is ux is. Ux is 2x minus 2. Okay. What is uy? Uy is minus 2y. So therefore, see, okay, another one. Uxx is what? Uxx is 2 and uyy is minus 2. So therefore, you see, uxx plus uyy is equals to 0. Therefore, Laplacian of u is 0, and hence this actually is a very nice candidate for the function to be analytic, because you see, if f is differentiable, then both the real and the imaginary part has to satisfy the Laplace equation. So you see, this actually satisfies the Laplace equation. So this is a nice function. Okay. Now what about v? What sort of v will guarantee that this function is differentiable? So basically, what happens is, in that case, u and v has a relation. What is the relation? CR equation. Okay. Now again, ux has to be vy. So there, now for f to be differentiable, okay, 2x minus 2 has to be ux equals to vy, right? And minus 2y has to be minus vx. So ux has vy and uy equals to minus vx. So these two has to be satisfied. This is gone. And this, from here, what does it gives you? V of xy is nothing but 2xy plus some function of x. Sorry, function of y. Right? V is arbitrary function. I'm just taking the integral with respect to x. Here also, if I take the integral with respect to x, what happens? V of xy becomes 2xy minus 2y plus v times x, right? This is the one we are getting. Yeah. not phi, let's write it as psi. Let's write it as psi times x. Psi times x. Psi is arbitrary. I hope this is clear to you. Yeah. So we are just integrating the whole thing down, and this is what we are going to end up with. Yes. Okay. So now you see both is v. Both is v. Yeah. So this must have some relation. So in this case, what happens is 2xy minus 2y plus a function of x has to be equals to 2xy plus another function of y. Yes. So you see this is getting cancelled. Fine. What about now? You see it is saying that a function of y is equals to something containing y and a function of x. That will imply psi of x has to be 0 and phi of y has to be minus 2 times y. Yeah. Okay. So if this is true, therefore, if this is your v, what is your v? V of xy will be nothing but 2 of xy minus 2 times y. Yes. And psi is 0. Okay. So that is what we are going to get. Therefore, f can be written as f of xy. Sanity, right? Sorry, f of z. F of z is sanity. It can be written as x square plus y square. What is it? X square plus y square minus 2x. Okay. X square minus y square minus 2x plus I times 2xy minus 2y. Yeah. So we can write it like this, which is going to be differentiable. Yeah. Okay. How do you guarantee that this is true? Yeah. So of course this is true because it satisfies the zero equation. You can also see that this v is the imaginary part of this function. So if you look at vxx plus vyy, vxx is what? I am not calculating this thing. Please do it. Vxx is nothing but, you see, vx. Okay, let me do it. Vx is 2y. Vxx is 0. Okay. Vy is, if you do it, it is 2x minus 2. Vyy is going to be 0. So vx plus vy is equals to 0, and hence this is going to be satisfy the Laplace equation, and everything is fine, right? So this is differential. Yeah. Now the main idea of this question is this. Let me give you another example. Example 2. Yeah. Please remember this thing. Not all functions can be done like this. Think of it like this. Let's say if I ask you this question, give me a function which is not differentiable. So of course you know that mod z sort of function, mod z square, those functions are not differentiable. Okay. But you can also construct other functions. Think of it like this. So let's say fz is uxy plus ivxy plus iv of xy. Yeah. See, if this is differentiable, that will imply that Laplacian of u equals to Laplacian of v equals to 0. Yeah. So if you start with a u, so if one starts with u, u of xy, which does not satisfy this thing. There are many things which does not satisfy these things. Let's say x square plus y square, this function, it does not satisfy that Laplace u equals to 0. Yeah. So any function whose real part starts have x square plus y square, that function cannot be differentiable. Yeah. So very, very simple. If I'm asking you to find out a function which is not differentiable, other than, let's say, generic mod z square, mod z, that sort of thing, then you can always do it like this, that you find a function such that Laplacian of u or Laplacian of v is not 0. You find some function like this and put it there, put it in the real or imaginary part, and then the same sort of thing works. Okay. So this function clearly f of z, which is x square plus y square, and I don't really care about what v is, because anyways u has to satisfy Laplace u equals to 0. Here it does not. So this plus I times some v. I don't care what v is. You can put anything v. This is not differentiable. So you understand that the idea of differentiability in C is extremely, strong. You understand? So it's not a very simple thing that you can just write it like in a one line thing and you are done. Yeah, it is very, very complicated. Okay. So now what we have is we want to see what CR equation does in polar coordinate. Okay, so think of it like this. Let's say, let's put another example. Fz equals to z power n in n. Yeah. Now I want to see if this particular function is differentiable or not. Differentiable. That's the question. Okay. So what do you do? The main, the most easy thing which you can do is you can do it like this. Write down in terms of polar coordinate. Write z is e power I theta. R e power I theta, sorry. R e power I theta. Okay. If you do that, then f of z, you can write it as r power n e power I n theta. Yeah. De Moivre's theorem, if you remember. Yeah, we can do that. Okay. So in that case, what happens? In that case, you can write it as r power n cosine n theta plus I sine n theta. Okay. Okay. So now what we have is we want to see that whether this particular function satisfies the CR equation or not. So we need to see if CR is satisfied. Okay. First of all, see here the function is no longer in terms of xy, but here it is in terms of r and theta. So here the real part is in terms of r and theta plus I, the imaginary part, is in terms of r and theta. And what is this u of xy? It is r power n cosine n theta, and this is r power n sine n theta. Is this okay? Yeah. So we have to find a CR equation in polar coordinate in this case, because the thing is the same CR equation won't work here. So CR equation in polar coordinate. Let's do this. Okay. So let's say that in polar coordinate, what is our x? X is r cosine theta, and what is our y? R sine theta. So in this case, what is u of r? Because I have to find out, see, we know the CR equation is in ux equals to vy, vx equals to uy in terms of x and y. I want to convert it to r and theta. So what is u of r? In this case, you use chain rule. It is ux and x with respect to r. Yeah, x with respect to r plus uy and y with respect to r. Yeah, so that will give you ux cosine theta plus sine theta uy. Again, v theta is vx x theta plus vy y theta. This is again given by minus. So you see, we are going to write this, what is x theta and what is y theta. So that will be vx sine theta plus vy r cosine theta. Yeah, I hope I'm doing the calculation correctly. Yes, I think x theta is r. Yeah, fine. Yeah, did I miss r somewhere? This is r. This is r somewhere. This is fine now. Okay, so you see, this is nothing but, if you write it properly, this is nothing but r minus vx. Yeah, minus vx. So ux equals to vy. So if we replace this thing, ux equals to vy. So you see, this is vx equals to minus uy. So this is minus vx is uy. Yes, minus vx is uy. Yes, and sine theta. Okay, and plus here you see vy is minus ux. Okay, So it is ux equals to vy. So plus ux times cosine theta. Yeah, which is nothing but this one. So it is r times ur. See? Yeah. Therefore, the polar form looks like this. Ur equals to 1 by r, okay, v theta. And similarly, you can do the other way also. And similarly, we also have that v of r is minus 1 by r u theta. Clear? So this you have to check it yourself. Please check it yourself. Okay? Check. And this is true. So you understand the polar coordinate, you can just change it like this. This is chain rule. Chain rule. Okay. So once you do it, now let's look back at our equation. This equation u and v. This is u and v. So u of r theta in this our case is now r power n cosine n theta, and v of r theta is r power n sine of n theta. Yeah. So that will imply that u of r is n r power n minus 1 cosine n theta. Okay. And this has to be equals to, and what is v of theta? Let's say v of theta, it is r power n, okay, sine n theta, right? So this is n cosine n theta. So you can see that ur is nothing but 1 by r v of theta. See? Yeah. So the first part is satisfied. You can also check the second part. So check the second part. Check the second part. Okay. So what did we deduce? We deduced that the function z power n. Yeah. Therefore z power n is differentiable for all n in n. Clear? This is always true. So what did we learn? We learned that a function f of z, you can write it as u plus iv. And in that case, what happens is, if it is differentiable, so this is a small remark, if it is differentiable in some domain omega subset of C, then ux is equals to vy and vx equals to minus uy. This is always true. Moreover, so this is CR equation part, right? Moreover, uxx plus uyy equals to vxx plus vyy is equals to 0. This is also true. Yeah. Okay. Moreover, we can also say that, you see, in polar coordinates, so basically if you change any complex number to the polar coordinate and then change the function in the polar form, then this is true, that ur equals to 1 by r v theta and vr equals to minus 1 by r u theta. Yeah. So these are the three things which you have to remember, and that will give you a very good idea of what differentiable functions is. Okay. So with this, I am going to end this video. In the next video, we are going to start talking about some more functions, because those functions are going to be very, very complicated. It's not very simple like z power n. Yeah. So I'm going to end it here. Thank you.